what do we notice about this? I guess, first of all, we've combined everything together. You could further simplify, right? You could take that k. First of all, AC you could divide out. You could take that k over delta x and form a group, and then put the ti's and ti plus 1s together. You could do that. The other thing to point out is that this gives you a number of equations, right? Every node is going to have its own set of equations that go with it. Here we've just developed an equation for node I, but this gives us, n minus 2 equations. So if we're going to solve a system of equations, we're solving for n temperatures. We have n minus 2 equations. We need 2 more equations to solve the system. Right? And this is where ease becomes really, really good. So, okay, maybe you can guess where we go next, and that is the other 2 equations. Questions on this?
Does the q dot not have a negative sign?
So the q dot we've drawn coming in, and so when we did the energy balance, the question was, does q dot not have a negative sign? We drew it coming in, so by our convention, everything going in is positive. In reality, like one of those is probably going to be negative, right, in reality. But as long as the convention we chose, which is coming in, matches the way we wrote the temperatures, right? We wrote the temperatures as higher to lower, right, out to in, then it's okay. Yeah. Yeah, because the question was, why not just apply this for every node? It's because the n nodes are different. That what we said for conduction here, like this one here, on the left-hand node is not valid because there's not conduction coming in. There's a different boundary condition. And the same is on the right-hand side. So on the right-hand side, you couldn't do the second term. You have to do something else.
Is the AC and the G dot equation just between the blue and the green lines?
Yeah, so the question was, is the AC between, so you're evaluating it at the node, is that what you're saying? Yeah, so is the AC, which AC is it? For this problem, it doesn't matter because it's a constant cross-sectional area. If it was changing, you would actually need to compute the actual volume of that, and so you might take the average of the 2 cross-sectional areas and then multiply that by dx, right? That would be a good approximation. Or maybe there's like an actual formula you could use for it. Anything else? Okay. So let's do the n nodes, and you'll kind of see how this wraps up. So we need 2 more equations, right? We have n minus 2, we need 2 more. Our 2 equations are coming from these boundary nodes, node 1 and node n. So starting with node 1, let's again draw our control volume. So I'm going to do it like this. I'm going to note now this width, the width of the control volume is delta x divided by 2. We have a different width for the node because it only needs to be responsible for that last bit, right? The last half control volume. So it's delta x over 2. All right, so we can write out like another equation here. So let's kind of skip the steps of q dot left and right, but just think about what those are. So starting with q dot left, what is q dot left in this case? 0. It's adiabatic. So 0. Plus, what is q dot right? Well, that's going to be, again, conduction, KAC, from T2 to T1 over delta x. The distance to conduct is still delta x, 2 to 1. Yeah, so that's the only thing that changes. So then, let's see, the generation, g dot triple prime, we're doing that, evaluating that at x1. Oops, x1. And what's the volume? Right, the volume is actually delta x over 2 times AC. So be careful, right? The distance to conduct is still delta x. The differential, or the control volume width is delta x over 2, which changes the volume, right? Question? In the first term, no. So that the question was, should the first term be multiplied by 2? The distance to conduct is still delta x. Right? Distances from node 1 to node 2, they're still separated by delta x. In the case of, like, if you had heat loss to the surroundings, like if this was a fin, you'd also have delta x over 2 involved in that area, right? The area that's convecting to the surroundings. So this is where people mess up. The areas, right? Is it delta x over 2? Is it AC? Is it AS, right? All the different areas are involved. Okay, so we have now n-1 equations, right? We just added another equation for node T1. What about this last one? So we can do the same thing. Coming in from the left, we have conduction from n-1, so that's K, AC, T, n-1, minus Tn. Again, I'll point it out again, but the order of the temperatures has to match the direction that you've assumed for heat flow. So we assumed it's coming in. That means it's coming from n-1 and going to n. So you have to write the temperatures in that specific order, out to in, right? Okay, so again, then the distance to conduct is delta x. Okay, so to the right, what do we have going on to the right? We said there was convection. So now I need a rate equation for convection. That rate equation is h bar times the surface area that's exposed. In this case, it's also AC, right? AC times the temperature difference. So this is going to be the difference in temperature between the ambient and the end node. But again, we're drawing stuff coming in, right? We're drawing everything going into this control volume. So I'm actually saying like heat's flowing in this direction, in to n. So that's saying T infinity minus Tn. Be careful with that, right? Make sure you follow the directions, the direction of heat flow. Then the last thing is generation. So that's, again, G dot triple prime evaluated at xn times the volume, which is delta x over 2 times AC, all equals to 0. All right, so we have n-2 equations from our internal nodes, 2 more equations for the end nodes. If you take that set of equations and dump it into ease and solve it, it will give you back the temperatures. Okay? So we're out of time. I think there's an office hour in here starting now, so stick around for that. And then we'll wrap this up next time. Thanks.